Okay, well, my watch says it's 3 minutes past 7, so let's start this evening's event. So welcome to this Audio Engineering Society UK section webinar. This event is open to all, and if you're not yet a member, please consider joining over 14,000 audio professionals worldwide. Our guest speaker tonight is Dr. Geoff Martin, Senior Technology Specialist in Sound Design at Bang Olufsen in Struer, Denmark. In tonight's talk, Geoff will open up the design and history of the Bang Olufsen Beolab 90, the first speaker model to use digital signal processing to actively control its radiation pattern, and why directivity is so important. The talk will include early prototypes, some of the lessons learned through its 8-year development history, and ultimately the final result. We will also be treated to a tour of B&O's main listening room, a large BS 1116 room situated in Struer, Denmark, including its construction and use in the development process. If you have any questions, please use the Q&A button at the bottom of your Zoom screen, and Geoff will be more than happy to answer them after his talk. So that's enough for me. Time now to hand the Zoom over to Geoff. Thank you.
Hi, I'm going to start sharing my screen here. I assume that you can see my PowerPoint presentation. Neil, can you see it, I guess?
Yes, can.
Great. Just a little bit of an introduction about me. I'm originally from St. John's, Newfoundland, where I stayed for a little while and did my Bachelor of Music in pipe organ with some choral conducting on the side. And then I moved to Montreal to go to McGill, where I did the master's degree there as a tone meister, which for those of you that don't know what a tone meister is, it basically is the same as mixing a recording engineer and a producer into one so that the people doing the recording can save some money. And finally, I stuck around at McGill to do a PhD in acoustic simulation. And when that was done, I moved to Denmark in 2002 to start working at Bang & Olufsen, originally in the automotive department, working on the new car prototypes that they had at the time. And then a couple of years later, I moved into home audio. Since then, what I've been largely focused on is algorithm design and what we call sound design, which most people would call loudspeaker tuning, but also doing quite a bit of work on specifications and measurements, and then education for our internal colleagues, as well as communications. We get a lot of visitors here to the big listening room, almost weekly, actually. So I'm doing shows like this one quite often for visitors. And then when I get really bored or I find something new that I've never thought of before, I start writing about it on my own website at tonemeister.ca. And there's a lot of stuff there, including some of the stuff I'll talk about tonight, because B&O lets me talk about the technologies that we're working on here on my own website. What I'll do, I think, to start is to talk a little bit about some ancient history, but we'll start, I think, by just looking at the room that I'm sitting in. I'll do that by stopping the sharing. This room is a BS 1116 room. It's not normally this full. We've got a lot of stuff in here for this show tonight. Normally all of these prototypes aren't here. The room is about 7 meters wide, 9 meters deep, and 3.8 meters high. It's a 26-ton airtight steel box floating on neoprene blocks, and that's sitting inside a 17-ton airtight steel box that sits on the concrete foundations of the building. So we're floating relative to the rest of the world. This room has its own dedicated air conditioning system. We've tried to find out how quiet it is in here, and what we can see is the noise floor of the B&K mic that we're using to try and find out what the noise floor is. So at least in the mid-range and high end, we really don't know how quiet this room is. The panels you see on the walls are all designed by IAC Acoustics. They're designed to absorb sound. They're all membrane absorbers with bass traps behind. And they're all movable, so we can just move them on the cleat that they're hanging from. Those have been verified from an outside consultant to follow the BS 1116 standard. So the room itself, from 40 hertz to 10 kilohertz, has a reverb time of 0.3 seconds flat. That makes it a really good room for working on loudspeaker prototypes, which is what it's for. So when we're at the end of our development process, the prototypes, or the almost production models, come in here, and we find out what's left to fix in the speaker itself. Unfortunately, this room, because it's so dead, is a bit useless for tuning domestic loudspeakers. So once we're done in here, we have to move into other rooms to do the final sound design of the speakers. So we have a room next door that is built the same as this one, a steel box on springs inside a steel box, but it follows the IEC 268 standard, which is more like a normal domestic living room, whatever that means. So typically what happens in the development process of any loudspeakers, including this one, if we were to do it today, we would do the final prototype in here and then move into usually 3 or 4, maybe 5 more normal domestic rooms to check and see that not only the sound design is working, but also our room compensation algorithms are behaving. That's the room itself. Inside the room, we've got some features that will look very normal for many people. We have the curtains to keep us honest. So normally once a week, one of us in the acoustics department will put something behind the curtains. The curtains are made out of the same fabric we use to cover our speakers. So it's acoustically transparent. We're about 1 dB down at 20 kilohertz. So that's fine. So one of us will put something behind those curtains, and the rest of us will sit out here in the big part of the room, listening to whatever's behind the curtain, and not only commenting on whatever characteristics we can hear from that speaker, but also learning from each other. We bounce a lot of information back and forth within the group in the acoustics department. Some of us are better at hearing port chuffing, some of us are better at hearing resonances, and we use those sessions not only to evaluate our prototypes, and in some cases the competition, but also to learn from each other. And then the rest of the room, we have a pair of Beolab 90s that live here constantly. Those are the 2 that are in the normal position. The TV just below that is our soundbar, which includes a full Atmos decoder. What most companies would call a surround processor is built into that. And then that's connected not only to the Beolab 90s, but also 6 smaller speakers on the walls. You can see here, those are connected wirelessly using our implementation of a WISA connection. So those are six speakers on the walls connected wirelessly, and then 4 more on the ceiling, which are connected with a wired connection. So we have a full Atmos system in the room. Ooh, panning. There we go. So we have 4 up in the ceiling, and then essentially 7.1.4 coming into the room, and 7.0.4 going out, because the LFE channel is being sent to the Beolab 90s instead of to a subwoofer. That's the room. So let's start talking about some history. Most of what I'll talk about tonight involves the directivity of loudspeakers. That's not a new issue at B&O. And the reason is that most of our customers don't sit in the sweet spot listening to music. Most of our customers have loudspeakers in their living room, they turn them on, and then they go make dinner. So to be perfectly honest, we're not as interested in the on-axis frequency or magnitude response of our loudspeakers as we are about the power response, filling up 3-dimensional space in the room, because most of what our customers are hearing most of the time is the 3-dimensional radiation from the loudspeaker bouncing around the room and then leaking into the kitchen. And that's been true for a long time. If we go back to the early 1960s, this was a speaker that was released in 1961, 62. And what's under here, this was designed to be an addition to a bigger loudspeaker. So you just bought this and plunked it down on top of a big 2-way speaker. And what is inside that is what in those days would have been called a tweeter. So we can see there's a tweeter here and another one here, and those are aimed at reflectors. So the idea being that although the tweeters were aimed vertically, this, in theory, would radiate the reflection out in a three-dimensional world, basically as a 360-degree radiation in the horizontal plane, making it more like an omnidirectional tweeter to give us a better power response. So this is what was being done, in the 1960s. So that puts us back 60 years ago. So even then, you can see that B&O was thinking about, we could say, power response, but more specifically the directivity of our loudspeakers. If you fast forward about 6 years, we get to about 1967, 68, and that first solution was replaced by this one. This is just 6 drivers, all connected apparently in parallel. They're not really in parallel, but they behave as if they're in parallel. And so the idea of this, again, was to make a three-dimensional omnidirectional radiator. Of course, it's not omnidirectional. Of course, there's going to be lobing. Of course, it's just an analog system. But still with the idea that the three-dimensional radiation of this driver set was more important than the on-axis frequency response at one location. Again, with the idea being that this would drive sound out into the room in all directions, rather than simply make one sweet spot for somebody with one chair and no friends. So that was about 1967. And then if you fast forward to about 2000, leading up to 2000, the concept was essentially enhanced again with Beolab 5. This was our flagship speaker that was released in 2002. They were just doing all the press events when I first got here in 2002. This one used a system a little like the early one from the 60s, where you have a mid-range and a tweeter that are aimed upwards at a reflector. And the reflector is, on a cross-section, an ellipse, with the idea being that the driver was in one focal point of the ellipse, and you have all the sound therefore being reflected from the second focal point. But that ellipse was rotated 180 degrees, so that what's happening is that the sound is coming from the mid-range and from the tweeter and bouncing out to form a half disc shape, if we're generalizing a little broadly, to give a very wide dispersion in the mid-range and high end, yet a fairly tight beam vertically. That was the idea behind this design. And that was the result of trying to build a speaker that followed the research that was done in what was called the Archimedes project, where they looked at using a simulated room in an anechoic chamber, where they had a lot of speakers placed around a chair in the middle of an anechoic chamber. The question was, if you have a direct sound, how loud does a horizontal or a vertical reflection have to be before it affects the timbre of the direct sound? And what was found in that project was that a reflection coming from the vertical plane has a bigger influence on the timbre due to comb filtering than if it's coming from the horizontal plane. So we get away with a wider dispersion speaker horizontally than vertically. The other advantage of making a speaker that has a wide horizontal dispersion is that your power response, which is the three-dimensional radiation of the speaker, starts to approach your frequency response or your on-axis response. In a perfectly omnidirectional loudspeaker, then the on-axis response and the power response are the same thing. And the more directive your loudspeaker and the more directional the pattern is with a frequency-dependent directional behavior, then the less your power response and your on-axis response match each other. If we look at the behavior of the Beolab 5 in terms of how it measures, then we see a plot like this. So this is how we normally look at the directivity of our loudspeakers. You can read this basically the same way as a topographic map. So we're looking at the on-axis response, whatever that is, and we normalize to that. And we call that, regardless of frequency, we call that 0 dB. And then for every dB that we drop coming around the speaker, so you can see for the Beolab 5 at, let's say, 200 or so hertz, we get 1 dB down at about 45 degrees off axis. But at another frequency higher up, we get to that 1 dB down at a smaller angle. So you can see it's narrower here than it is here. So we're often looking at these topographic maps to get an idea of the directivity pattern of our loudspeakers. This is the horizontal directivity. Of course, we'll also make a vertical directivity as well. The whole idea behind Beolab 5 at the time was to make as constant a directivity as possible. And what that means, at least here where we live, is that the directivity of the speaker is frequency independent. So our real goal with this loudspeaker is to make these lines as parallel as possible. And the reason for that is to ensure that the off-axis response matches the on-axis response as closely as possible. As soon as you have irregularities in the width of the beam and the directivity of the loudspeaker varying with frequency, then what that means is that your off-axis response, let's say here at 90 degrees, we can see down at the bottom, we're within a dB of the on-axis response. And by the time we get up to something like 600-700 hertz here, we're about 14 dB down. So you can see that we really become narrower in that frequency range and then wider again. And what that means is that if you are 90 degrees off axis to the speaker, then you have a strange frequency response or magnitude response relative to the on-axis response of the system. So the more we can make these lines parallel, then the more the loudspeaker will sound like itself as you move off axis, and the more in that case, the more the reflection that's coming off the sidewall will have the same magnitude response as the on-axis. Like I said, we look at plots like this every day, so they're pretty normal for us. This is 1 dB per contour in this plot. And like I said, it's normalized to the on-axis response. It may be more normal for a lot of people to see it as a waterfall plot, which looks like this. This is exactly the same data, just plotted in a different way. So what we can see here is that it's really obvious that that top line, which is the on-axis response, has been set to flat. In essence, because we have full DSP in our loudspeakers, we can choose what the on-axis response of the speaker will be. And so that's something we can decide afterwards. But the directivity of the loudspeaker, that's dependent, at least in terms of the Beolab 5, on primarily the shape of the loudspeaker, the hardware itself. To some extent, it's dependent on the crossover as well. But in essence, as I said, this plot and this plot show us the same thing for Beolab 5. And that's what we were doing, let's say 22 years ago, roughly. If we deviate from that a bit and look at a slightly different version of reality, and talk about how we perceive distance. So if we're looking at how we perceive the distance to a real source in a real space, and you go look it up in Brian Moore's book. This is an old copy that I've had on my shelf for 25 years or so. He starts this paragraph talking about how we detect distance in an anechoic space or outdoors. And he says the obvious, that you can tell things are further away when they're quieter and when the high end rolls off a bit, especially on foggy days. But indoors, we determine distance to a real sound source, like somebody speaking to you, by comparing the ratio of the direct to the reflected sound. In studios, we call that the wet-dry mix. But in real life, what we're really listening for is the level of the direct sound to the level of the reflected sound. And we're using the time delay between the direct and reflected sound. And this tells us how far away something is in a real room indoors. That's not only true for a real source like somebody talking or a musical instrument, it's also true for a loudspeaker. But if we look at how a loudspeaker behaves with respect to directivity, if we do nothing but put a driver in a box. So this is going way back to Harry Olsen's book from 1957. He shows the theoretical directivity of, in this case, a 16-inch driver with a 110-degree cone. It doesn't matter because it's roughly the same if you have a piston or a dome. They all have basically the same behavior, where at a very low frequency, where the wavelength of the signal is large, or is roughly on the same order as the size of the driver itself, or larger, then you basically have an omnidirectional radiator. So as we can see here, for a low frequency, we're less than 3 dB down at 90 degrees in this case. And as we go higher and higher in frequency, we get a narrower and narrower beam. We start becoming a lot more directional, because the wavelength of the signal that we're emitting is very small relative to the diameter of the driver itself. This is a natural behavior of how a driver, like a piston, will radiate sound into half space. If you then take that driver and match it with a smaller driver, so you make a two-way speaker, what happens is the woofer will be omnidirectional at the low end and start to beam as you get higher and higher in frequency. And then you go through the crossover and get to what is effectively the low frequency of the tweeter, where it goes omnidirectional again. And then that starts beaming again. So we have something that's omni and then beaming. And as you move across the crossover, omni and beaming again, for the case of a two-way loudspeaker. If we look at that behavior, but consider it in terms of a direct to reverberant or a direct to reflected ratio, you get a plot that looks something like this. And this is from Howard and Angus's book from, again, about 20 years ago or so. In the very low end, where you have a low frequency signal that is radiating omnidirectionally, then you have basically as much reflected energy as direct energy. And as that woofer starts beaming more and more as you go higher and higher in frequency, then you get less and less reverberant or reflected energy until you hit the crossover, where you go into a smaller driver, which becomes omnidirectional. So you get more reverberant energy or reflected energy again, and then that starts tailing off as the tweeter starts beaming. This is a natural behavior of a two-way system. If you've selected a crossover point where you've gone higher than a frequency where the woofer is going to be omnidirectional. So if I'm assuming here that you've picked a crossover high enough that the woofer started beaming. But if we go back to Moore's original statement about how we determine distance in a real room, that means that this plot doesn't just show us the direct to reverberant or the direct to reflected ratio. It also gives us an indication of how distant things sound when you're sitting and listening to the speakers. And this is something that if you're sitting in a listening room and listening to, let's say, a recording of solo voice, let's take Suzanne Vega singing Tom's Diner as an example, because that's what we all listen to when we listen to voice. With a loudspeaker that has this characteristic, you'll notice that the voice starts pulling apart in terms of distance, meaning that the formant, not the formant, but the fundamental of the voice in the low frequencies will sound as far away as the speakers, because you have roughly the same amount of reflected energy as direct energy. You get a lot of information telling you how far away that loudspeaker is. But as you move further and further up in frequency, the woofer is beaming more and more, you get less and less reflected information. And the voice, or at least those components of the voice, start appearing to be closer to you than the loudspeakers themselves. And then when you get a little bit higher again, you get into the tweeter. And then the bottom end of the sibilance, let's say, if that happens to be where your crossover is, move back further away again. And so what's happening is that the perception of the distance to the phantom image is getting pulled apart in distance, where some frequency bands are as far away as the loudspeakers, and some frequency bands are closer than the loudspeakers. You can't go further away than the loudspeakers without considering the reflections that are in the mix itself. So if we're talking about an anechoic recording, like it's anechoic-ish at least, like Tom's Diner, then you get this effect. And the more you start to notice it, the more annoyed you get by it. You won't find this to be a problem if you're in an anechoic chamber. You won't find it to be a problem if you're outdoors, because there's no reflected energy to tell you how far away the speakers are. Also, if you're used to listening to electrostatics or dipoles, you won't have this complaint either, because typically with a dipole, there's such a reduction in the sidewall reflection because of the dipole directivity that you'll notice everything sounds closer than the loudspeakers. In effect, what's happening is that the dipole is giving you a much higher direct to reverberant or direct to reflected ratio, and that's making everything appear to be closer than the loudspeakers, in the same way that any loudspeaker would sound if you were in an anechoic chamber. So that's one issue, is that we have known for a long time that we want a constant directivity, or a loudspeaker that has the same directivity, whatever that beam width or directivity is. We want it to be constant with frequency. And if we want to have an image that appears to be closer than the loudspeaker, as it would be in a room that has absorbent sidewalls, then we're going to have to make a loudspeaker with a narrow directivity. While we were thinking about that, we also were trying to solve a different problem. Now, this is completely unrelated to the issue that I just mentioned, but it is directly related to directivity in general. This plot is fairly well known to people who make loudspeakers. This is what happens if you have, all other things being equal, a two-way loudspeaker with two omnidirectional drivers, and you put in a fourth-order Linkwitz-Riley as your crossover, and then you normalize the power response measurement, meaning the three-dimensional radiation pattern, or the three-dimensional radiation response of the loudspeaker. If you normalize that to the on-axis response, you'll see a dip around the crossover. And this is caused by the fact that the two drivers aren't coincident in space. It helps a little bit to make them coaxial, but still that won't solve the problem. The problem is that if you're looking at the power response and you've equalized the on-axis response of the speaker to be flat, then you will have this dip caused by the separation of the two drivers. Those 4 curves that are shown there are for different separations of the drivers, but regardless of how far apart the drivers are, we're just playing with how big that dip is. And like I said, because we're Bang & Olufsen and because we're worried about the power response, we have two choices in this simplistic case. We can either make a flat on-axis response speaker and live with this dip in the power response, or we can fill up the dip in the power response and live with a bump in the on-axis response, or do something that splits the difference, have a small dip in the power response and a small bump in the on-axis response. There's all kinds of things you can do to play with this, but unless you have two coincident drivers that are omnidirectional, then you're going to run into trouble here. Of course, if your drivers aren't omnidirectional, if you do have some kind of directivity associated with frequency with those drivers, then that power response curve won't be flat. It'll be tilted downwards into the high frequency. So the higher up you go, the more it slants downwards. But the dip in that response will still be there. So this was an issue that one of our acoustic engineers had thought about for a long time, and he decided he was going to come up with a solution. So let's now stop sharing and go back to the live video, and we'll look at the solution that he came up with. That was this one. So if we forget about what's on top for a second, and we just look at from here down, this is a pretty typical two-way system that behaves as well as a two-way system can behave. This is just two drivers in a box. We connect those to external amplifiers. We connect the amplifiers to a lot of DSP, and we do what we want with the filtering. If we made this loudspeaker flat on axis, and then we measure the power response, we'll see that dip across the crossover. So the question was, how can we fill up the dip in the power response without affecting the on-axis response of the speaker? And the idea that my colleague came up with was to put a dipole on top. So what we have in the dipole is a tweeter and mid-range and a similar tweeter and mid-range on the other side, all connected individually. So we have, in essence, this is a 6-channel system. We make the two-way as if we were normal, and we pretend that that's true. And then what we want to do is fill up the power response, that dip in the power response that comes from the crossover, using the dipole. So all the dipole is doing is putting out energy to fill up that dip. But because it's a dipole and moving this way, in effect, then in theory, there's nothing going out the front. So what we can do is use the dipole to fill up the power response without affecting the on-axis response. That was the concept. If we measure this speaker, then the concept works. If we put this speaker in a very diffuse field, the concept also works. We get a nice smooth power response because this has fixed the problem, and we get a nice on-axis response because that's been behaving all along. However, in a real world, this thing sounds terrible. And the reason it sounds terrible is because we don't live in a free field with just the on-axis response, and we don't live in a diffuse field where this is actually filling up a power response and doing nothing else. Typically what happens with a pair of loudspeakers built like this is that you put them near sidewalls. And when you put them near sidewalls, you get an on-axis response from that part, nothing from here until it bounces off the sidewall and comes back. And this is what we realized pretty quickly, that when we have two of these set side by side, we got a very different response if we had the two dipoles on the left and right speakers moving this way than if they were moving this way. And that gave us our first really clear indication of being able to manipulate the perception of distance from a pair of loudspeakers to the, so you're sitting in the sweet spot, you're listening to a phantom image, and by controlling what these dipoles were doing, we could control the apparent distance to the phantom center because of the reflections off the sidewalls. So on the one hand, you could say this was a really good idea that was really terrible in implementation, but it wound up being the inspiration for what was to come. So in many respects, this was Beolab 90 Mark I. It sounds terrible. It doesn't work, but it gave us some hints as to where to move next. So where we moved next was this. This speaker originally wasn't an evolution of the two-way with the dipole. The idea behind this speaker was to try and accommodate people who move in their homes. So the question was, can we make a speaker that has an on-axis that we can rotate? So let's say, for example, you're sitting with a pair of these here. We call this the front of the speaker, but then you go to dinner and we then rotate and call this the front of the speaker. In essence, what we're doing is making a lighthouse. And that wasn't done by simply rotating from using these drivers to using these drivers. We're using all the drivers with some relationship between their magnitudes and their phases to make a beam. So in essence, we're doing beam forming. The beam forming means that we want to create a beam of some width and some direction. And we use all 6 tweeters, 6 mid-ranges, and 4 woofers simultaneously with different phases and amplitudes to generate the beam that we want. That was the idea. it worked reasonably well until you really started paying attention to it. And what happened was, the more you paid attention, the more you realized this was going to fail. It was destined to fail. The reason being that these drivers are simply too far apart. So we're getting lobing effects. This driver can't be used to control the amplitude of this driver off axis, which was our goal. The whole idea with beamforming is to use interference between the drivers. And unfortunately, because we're using these so high up in frequency before we get to these 1.5-inch tweeters, that we can see and hear lobing effects. And that was unavoidable because of the design of the speaker. On the one hand, our designers got really excited about the idea of having a loudspeaker that could rotate so that we could sit in different places in the room and still have an on-axis response in that part of the room. From the acoustic side and from the listening side, we weren't that pleased because it never really delivered the kind of performance that we were looking for, and certainly not what we were even getting from the on-axis response of a simple two-way in a dead room. So we said, what happens if we forget about the idea of rotating the beam, but we go with this idea of using beamforming and cancellation, constructive and destructive interference from all the drivers to make a beam that was as narrow as possible. This is something that Linkwitz, he used to call it headphones at a distance. So the idea here is to be a little like a dipole, but without the back lobe. And that's how we got to this version of the speaker. So the idea here was that we had 3 woofers, symmetrically or radially symmetrically arranged. Again, all of these are independent. Each has its own amplifier, its own DSP channel. Everything is completely separate. So it's not a 3-way speaker, it's a multi-way speaker because everything is behaving independently. As I said before, with the previous version, these 2 drivers are simply too far apart to reliably give us a narrow beam width. So we were getting lobing. So then the question was, how can we get these as close together as possible? And that got us to this solution. So if we're just looking in the horizontal plane, we have not just 2 drivers that are side by side, but one that's halfway between the 2. And so these 5 drivers together are making a single beam that's radiating outwards. And we had to have one more in the back as a cancellation against the back wall. So the idea here, as I said, was to make a beam as narrow as possible. What we also found when we made the previous version with the rotating speaker was that these 1.5-inch tweeters, although they behave really well up to about 10 kilohertz, we started losing control of them from about 10K and up, roughly. And so we started looking into the option of getting a super tweeter. Some people would call it, we would just call it a tweeter. This is an 8mm dome tweeter that we had made as a prototype. This never got put in any speaker, but we kept the prototypes. We still have a couple lying around. And that let us take care of the directivity from about 10 kilohertz and up. So what we had here was 3 woofers, 5 + 1 mid-ranges, so 6 of those, 6 tweeters, there's a tweeter in the back as well, and then 4 of those 8mm dome tweeters to look after the very top end from 10, 15K up to about 40 kilohertz. And as I said, every one of these is connected to its own independent amplifier channel and DSP channel. These all get measured in our pseudo-anechoic chamber and then brought into a listening room to have a listen. To be perfectly honest, these sounded amazing, but only if you had one chair and no friends. They're really unforgiving with respect to movement because that beam is so narrow. Of course, we could choose to make it more narrow, more wide, I mean. But what we lost in this was what we had here, which was the ability to rotate the beam. And ultimately, what we wanted as a final real speaker for our customers was something that bridged the gap between these 2 worlds. We wanted the narrow beam of this, if you're sitting on axis and you're listening actively, but the flexibility of this for somebody who wanted to go to the dining room and still have an on-axis-ish response. So those 2 concepts got merged into one idea. And that was the final prototype before we really started building speakers. So you can see what we wound up with now. Instead of 3 matched woofers, was 1 large woofer. I think that's a 10-inch, and then 3 8-inch woofers on a triangular arrangement. And in essence, what we're headed for here is using 1 woofer as the main driver and 3 more to control the directivity. Of course, they're helping provide output. They're not just being used for beam width control. So 4 woofers in total rather than the previous 3. We didn't want to use more drivers than we had before. So we had 5 in the front and 1 in the back before. We changed that arrangement to have 3 plus 2 plus 1. So we still have the 6 mid-ranges and 6 tweeters, 3 plus 2 plus 1. And what this did was gave us a speaker that had not quite as narrow a beam or as narrow a directivity as our previous version, but with the option of rotating. So we did have the option with this speaker of saying, this is the front. If you go to the dining room, you get a wider beam, but you can rotate it. You can't rotate it continuously like you could with the first version. You only had 4 options. So there was the front, the side, and the rear. So in an extreme case, you could say this is the front of the loudspeaker as well. And this is what we, in the acoustics department at least, decided would be the final version of the speaker. It turned out in the end that we didn't need this super tweeter or the 8mm dome, so that disappeared because we had such good control of the high end through these 1-inch tweeters that we wound up using. They behave better than the 1.5 inch up at the 30, 40K. But this is what we wound up with in the acoustics department. And we said, this is what we're heading for. And at that point, we started talking to the designers. Normally at B&O, the designers, the visual designers are brought in much earlier in the process. But at this point, we're now 4 years, I guess, into the process, give or take. And at this point, this is when the designers, the visual designers came in. We had the meetings and we said, this is what we would like to do. And I think for the first time in Bang & Olufsen history, the visual designers said, can we have more drivers? Normally they want smaller and less and fewer and tighter and smaller. And that's always what we tell people is a friendly fight, but it's not really very friendly at all. But what the designers then said was, what if instead of 1 driver in the back, we had 2? So 2 mid-ranges and 2 tweeters rather than 1 and 1. And of course, anybody who works in acoustics knows that if somebody gives you more of anything, you'll take it. So in conjunction with the designers, we wound up on the final driver configuration. So this is what eventually went to the visual designers. So this is the result of our acoustical engineers and our DSP engineers calculating based on the 3-dimensional radiation patterns, or sorry, the horizontal radiation patterns of these drivers individually in their boxes, calculating where these drivers needed to be in space to give us the beam forming capabilities that we wanted to make a beam that was as narrow as possible and as same as possible at as wide a frequency range as we could do. Of course, there are some limitations to how low we can go with using these drivers to cancel this driver off axis. If we wanted to go down to 20 Hertz, the speaker would have to be twice as wide, because what we start suffering from is that these drivers are simply too close to each other for this to cancel this. So we do have a low frequency limitation to the beam width control. But ultimately, this is what our acoustical engineers said to the visual designers and said, this is where the drivers need to be. And we're telling you how many liters of air we need behind each of these drivers. So each one is in its own sealed cabinet. And unlike most of our speakers that we develop, we got to choose how much volume was behind each of the drivers. So that was the model that was sent to the visual designers. We knew that this was going to have to live in a box with all of the processing, all of the amplifiers that that came along for the ride. Because when we make a speaker, it has everything built in. So this speaker not only has the drivers in their individual cabinets, but it also has all of the amplifiers, all the DSP processing, all of the power supplies that we need. So we knew that we had 7 tweeters, 7 mid-ranges, and 4 woofers. So as a result, we needed 2, 4, 6, 8, 10, 12, 14 smaller amplifiers. These are 300 watts each from Ice Power for the mid-ranges and tweeters. And then 4 1,000-watt amplifiers for the 4 woofers. And those 14 plus 4, 18 channels are driven by 18 DAC outputs on the DSP board, which are fed by 2 sharks. So all of our beamforming is done inside those 2 sharks as FIR filters where we need it, and IIR filters where we can get away with it. Of course, the directivity processing is done with FIRs. A lot of the equalization for resonances and the crossovers are being done with IIRs. And we have more stuff going on in these sharks that we'll hopefully get to at the end if we have time. That whole thing is being powered by the power supply, which is built in. And this has a microprocessor built on board to make sure that it isn't pulling too much current from somebody who lives, say, in Tokyo, where you have 100 volts at 5 in the afternoon. So what's happening here is that the microprocessor is charging up the capacitors, trickle charging, or trickle is a bad word, to make sure that they have the current capability that we need if we have a high spike at a high sound pressure level. We often tell people, the marketing tells people that we have about 8,000 watts here. That was done by just adding 300 plus 300 plus 300 and so on until they got to a number. The truth is that on a spike for about 3 to 5 milliseconds, we have about 18,000 watts in each speaker, but that decays very quickly as these capacitors start to discharge. So all of this is sitting on board the speaker, and I'll show you how shortly. But in addition to all of this, it's not just a single input to the speaker. We actually have 7 inputs. So we have 3 analog inputs plus 4 digital inputs, and that's what all of this is. So this is all feeding into the main circuit, the main DSP board, before it goes out to the amplifiers. So the drivers plus all the electronics had to fit in one box, and that wound up looking like this after lots of meetings with the visual designers. This is actually the second prototype that we made. In order to make the cabinet, this is cast aluminum or aluminium, depending on where you're from. It's cast into a mold that's originally made of a 5-ton block of steel, and they mill out 3 tons of steel to make the mold itself. The cavities inside, it's done with sand casting, so the cavities inside are done with sand that's put into the mold, and then the whole thing, they drop in about 150 kilos of molten aluminum. But once all the extra is milled off, then we get down to something like 60 kilos of aluminum for the cabinet itself. And this includes all the walls, the interior walls that separate this cabinet from this cabinet. They're all sitting in their own individual cabinets. So that's the main body of the speaker, which has the 4 woofers plus all the electronics inside. We'll get to that in a second. And then the head includes a lot of electronics plus the 7 tweeters, 7 mid-ranges. And this, I don't know, this one can I'll lift it off the other one when we get there. So this was our second cabinet that we made. We actually made a pair that looked just like this. And of course, as we do with all our speakers, this goes on our measurement rig, which is a crane that hangs from the ceiling of our pseudo-anechoic chamber. That's a 12 meter by 12 meter by 12 meter room, where there's a microphone sitting out in the middle of the room, and this thing goes out on a crane, and we measure it, rotate, measure, and so on and so on. And we found a problem with this prototype. The problem was that on axis, our main mid-range driver wasn't giving us a flat magnitude response like we expected, we had a dip at about 800 hertz by about a dB+. And it took us a long time to find out what was causing that. In the end, what we found out was that at least at 3 meters out, this driver radiates outwards, of course, but it also radiates vertically. And when it does radiate vertically, it hits this shelf, bounces, that gets out to the microphone, and that will cancel this at 800 hertz by about a dB. That was a problem for us. It was a bigger problem for procurement because we wanted this to go away. What we did was found out that this was indeed the problem. We 3D printed a small insert to go here to raise this shelf to get rid of the reflection, or at least direct it in a different direction. And that made the problem go away. But that meant in order to fix this problem, we had to start from scratch and make a new mold, which meant starting with another 5-ton block of steel, milling out 3 tons of steel to make the mold. And that was a long meeting on a Friday afternoon. But in the end, we got it. And if we look at the final product, it looks like this. So if I put these two side by side, you can see that the final version is slightly different. This shelf is now raised, and this is, in essence, a final version of the speaker. This one won't work because we've had it apart a couple of times. You can see that for maintenance, it's quite simple. This whole thing is hinged, so the whole head unit sits on a single hinge when it's loosened, and that just plugs into a single circuit board. So all of the electronics up here are easy to replace or at least repair. And if we turn it around, you can see that the all of the rest of the electronics live in what we call the engine bay, and that's here. So they're also quite easy to repair. This is the power supply. There's the DSP board, and the rest are mostly amplifiers. The beautiful thing about this is that all of the electronics are separate from the acoustic cavities. So any pressure changes that we get inside the speaker aren't transferred into this area of the speaker. So there's very little vibration on any of these PCBs. The other nice thing is that this gives us a lot of heat transfer to the outside world. There is quite a bit of heat, for example, coming off that power supply, and we can radiate it out quite well because we have so much aluminum there. We've just got it bolted with a thermal connection directly to the outside. So in the end, we have that speaker, which as a pair, looks like what you see behind you here. So naked, it looks like this. Most customers, I don't know of any customer that would actually have it like this. It's the way we keep it here in the listening room because it's easier to point to things when we do shows like this one. But in a customer's house, it's more likely to look like the one on the other side. One of the issues that we had was that we had to negotiate with the designers. They wanted this tent shape over the head unit, but we had to make sure that the supports for that fabric weren't causing diffraction problems from the tweeters. So when you put something hard, like this wire, in front of the tweeters, this becomes a new source. In a normal case, if this was just a 3-way loudspeaker, this wouldn't be a big issue. Yes, it would be causing diffraction, but it wouldn't be horribly detrimental. However, because we're using beamforming from these tweeters, this becomes a huge problem because it affects the phase relationship of the drivers out in space and causes our directivity to go a bit out of control if this wire is too big. So we gave the designers a maximum allowance of 5 millimeter diameter on this wire. So they had a bit of a challenge there as well to make sure that they could design a hat or a grill that could live on top of the speaker without messing up the directivity control that we wanted to implement. That's it. So now let's go back to the PowerPoint and take a look at what the final measurements look like. So This is, again, that two-dimensional but 360-degree measurement of the directivity of a competitor speaker. This was one of the things we benchmarked as a competitor when we first made Beolab 90. And what we could see here is that although this speaker gets pretty good reviews and actually, to be frank, sounds quite good, there isn't much control of the directivity or the beam width in the horizontal plane as a function of frequency. And if we look at that as a waterfall plot, oops, it looks like that. What we wanted was a much narrower directivity and a much more frequency independent directivity. In fact, what we were aiming for was 20 dB down at 90 degrees off axis. So we were looking for something like this. This was our target. This is showing 14 decibels, or maybe that's 12. But in essence, what we want is a frequency independent directivity that's as narrow as possible and therefore as same as possible at all frequencies. If we look at the final behavior of Beolab 90, it looks like this. So this is what's actually coming out of the speaker when it's in narrow mode in a day-to-day use case. So we came quite close to our target, but as I said before, because the woofers are too close to really behave down at 20 hertz, you can see that, of course, things start to spread. If we wanted to control the directivity all the way down to 20 hertz, we would have to make a much bigger speaker, and then we would have to make bigger doors to get them through. That was one of the limitations we had with this, was it actually has to get installed in customers' houses. If we look at that as a normal waterfall plot, oh, sorry, it looks like that. But if I go back one, if we think of Beolab 90 not as a speaker with 18 drivers and we're using beamforming to control the directivity, if instead we think of it as a three-way speaker with one woofer, one mid-range, and one tweeter, and everything else is being used to control the directivity, what would happen if we turned off all those other drivers? And the answer is this. So this was one of the questions we asked, and I can explain why we asked this question when we get to the end of the presentation. The question is, what if we turned off the directivity control and just left three drivers on, woofer, mid-range, tweeter? What would the behavior of the speaker be like? And the answer is this. No customer can do this. This is not a setting that's possible on the speaker, but it was an interesting experiment for us. So this is with beam control off, and there it is with it on. This is the normal behavior of the speaker. But as I said before, the flagship speaker that we had before this, before Beolab 90, was Beolab 5. And Beolab 5's goal was to make a wider beam so that we had a bigger coverage of the, say, the customer sofa listening area with mid-range and high frequencies. And we were assuming when we made Beolab 90 that there would be customers who already owned Beolab 5 and who would move those into the surround locations, keep their old speakers, move them as surround speakers, and put in Beolab 90s. And in that case, what we wanted was a Beolab 90 that had the same directivity, the same beam width as the older speaker, as the Beolab 5. The good thing is that because all of this directivity control is happening in FIR filters in the DSP, then we could design whatever directivity we wanted within reason. So we set a second target, which was a wide setting with a very different behavior than the narrow setting. And that's, in the end, what we achieved. Again, this is 14 lines at 1 dB per line. And this directivity was designed to be a match to the Beolab 5, but a slightly more controlled version. If you remember the Beolab 5, it had a much wider directivity in the bottom end, and it was a bit more irregular around 1 to 2K. What we have a more controlled wide beam. And then a waterfall plot that looks like this. And you can see that there is some lobing going on. We get a little bit of a spike up at, say, 3-4 kilohertz off axis slightly, say 30-40 degrees off axis. But this is a minor issue. And there is some lobing as well in the top end where we get some beaming coming off the sides relative to the on axis. One thing to consider with both of these cases, both the narrow case and the wide case, is that we're using a lot of energy fed into the amplifiers to cancel sound in some direction. In both cases, we're canceling sound in the rear of the speaker. In the narrow mode, we're also canceling quite heavily to the sides. And therefore, in both of those cases, what you have is a speaker that's not very good if you're throwing a party. And so what we made was a third directivity, which we called omni mode. You can see here that it's not omnidirectional, and there was never any real intention to make an omnidirectional speaker. This is more a background music party mode for what is basically intended to be a narrow or wide speaker. And so you can see here, of course, there's an enormous amount of lobing going on from about 5 kilohertz and up. That's because those tweeters are just so far apart from each other that if you do use them to send energy in all directions, there's no avoiding the lobing. Of course, if we wanted to make an omnidirectional speaker, it would have been a very different hardware configuration. So like I said, there was no real intention to make an omni speaker. This is just a party mode for what is effectively a narrow and wide speaker. And the lobing, the irregularity of that high end can really easily be seen here in the waterfall plot. This obviously is not a speaker for listening to. This is a speaker for throwing a party and having a glass of wine with, and maybe dancing too. That pretty much wraps it up for the beam width control, but I haven't really talked about, and I'm not going to get much into, the fact that we still had that leftover from the hexagonal speaker, the lighthouse, where we could rotate the beam. That's still the case with Beolab 90s. So a customer can move the beam into one of 5 directions. So it can be front left, front right, rear left, rear right. But because we only have one driver in each of those directions, we don't have the cluster of 3 like we have in the front, then the only beam width that can be rotated is the wide beam. So you can have it in narrow mode, which is only out the front. You can have it in omni mode, which is lobing but sending sound everywhere. And in the wide mode, you can choose one of 5 directions. And I'll show you on the next slide, I think it is, how that's done in the user control. That's how we're dealing with, in effect, what I've started talking about, which is the direct to reverberant or direct to reflected sound. Of course, none of that looks after issues with room modes, which are always a problem, of course. And so one of the additional features that Beolab 90 comes with is an active room compensation. When they get installed, the customer or the installer will plug in a microphone that can be attached to the back of the speaker. And it runs a sine sweep on each individual driver, and then calculates what the response of the speaker will be in each of the directivity modes that I just explained. It can then, what it's really doing is saving the measurements. And so as you change as you create different presets with different directivity modes, it'll calculate a new room compensation filter that's appropriate to the directivity of the speaker settings. Because if we just did one room measurement in narrow mode, that wouldn't be applicable to the omni mode. You have to make a different measurement for the omni mode. You can either then choose to measure each mode individually, or you can measure each driver individually and calculate what the resultant will be after beamforming. So that's built into the speaker as well. And as I'll show you in a minute, you have multiple choices for those different room compensation filters. It also includes a 7-band parametric equalizer. If the room compensation is not doing everything you want it to do, you can always customize it a little further with a built-in 7-band parametric EQ. And as I said at the very beginning when we were looking at the electronics, we have a total of 7 inputs, so there's no need to get an external, surround processor or AVR, for example. You don't need to get a DAC. You just plug in an SPDIF or an XLR input from a source, and then you use the speaker itself to switch between those sources. That's done, or it can be done in a number of different ways. This is a shot of the web interface that comes from the speaker itself. So all I had to do to get these was to put in the IP address of the speaker. And you can see here that you can choose between which input you're using on one page. You can choose between which preset you're using and the volume, and there's a mute here as well if you want to stop listening. And if you go into any of these presets, then from there you can choose which beam you're using, whether it's narrow, wide, or omni, and which beam direction for the wide mode. You can also optimize for where you're sitting, and that's optimized using a distance and a level of each speaker to the listening position. And then, as I said before, we've got a 7-band parametric EQ and the room compensation. The room compensation is fairly flexible. You can make up to 5 different filters, and each of those filters is made with 3 microphone positions. So you put the mic in one position, you run the sweeps, you move the microphone, run more sweeps, move the microphone, run more sweeps, and now you've got a measurement for one filter. And so you choose as a customer where the microphone goes. You can keep them clustered around the listening area, or you can put one in the kitchen, one in the living room, one in the dining room, if those are your 3 microphone positions. Those each of those room compensation filters then is made with 3 microphone positions. You can make up to 5 filters or 5 sets of measurements, and then you can combine any 3 of those to make a filter for the room compensation. So in the case you're looking at here, I made one room compensation measurement called listening room A, which is a fairly wide placement of microphone positions, one called sweet spot, and another one called listening room A, full room. But I'm using all 3 of those sets of measurements, so that's a total of 9 microphone placements to make one filter for this preset. And so what that means is that our installer can come in and do all of these measurements for the customer, but the customer can choose which measurements to use to make the room compensation they want after the installer has gone away with the microphone. The only other thing I would add to all of that is that there's a latency issue to be discussed. As soon as we start using FIR filters to do beamforming to control directivity, then there is a latency implication. In essence, we need to use time to ensure that we're controlling the phase and the magnitude of each driver correctly. The problem with that is that if we want to control the directivity of the speaker down to 40 Hertz, then the FIR filter has to be very long. So we have to have 2 latency modes. Normally, if you're just listening to music, where you do want to control the directivity down to 40 Hertz, then the latency of the system is 100 milliseconds from analog input to acoustic output. If, however, you need lip sync and you don't have a Bang & Olufsen television, then you need a low latency mode. And so what we're doing there is we have a latency mode of 25 milliseconds, or 29 milliseconds, which still has lip sync, but the cost of that is that we lose directivity control in the very low frequencies. We are using different FIR filters for the low latency mode than the high latency mode. But the simple version is that if you need to have lip sync, because you don't own a B&O television, then you have to go into this low latency mode, and the cost is low frequency directivity control. On the other hand, if you do have a Bang & Olufsen television, then our televisions know what the latency of the speakers are. And so those can pre-compensate all the other speakers in the system to ensure that everything is in sync. So one of the advantages of being Bang & Olufsen is that most of our customers only buy Bang & Olufsen. And so that means that our loudspeakers and our televisions know what each other's capabilities are and can compensate on a speaker by speaker basis, or in some cases a speaker to video basis, to make sure that we have synchronization across the whole system. I think that's it. It's probably enough from me. And I guess now I hand it over to you, Neil, so that we do the Q&A, or what happens now?
Well, thank you, Jeff. I think first of all, it's a big thank you from the Audio Engineering Society. That was a really interesting talk. Covered a lot of material, very in-depth, and definitely, while you were talking, I looked up the price of the Beolab 90 speakers, and
I knew somebody was going to ask.
I don't think I'd get away with buying a pair for now. Maybe if I win the lottery. I think someone did ask. Yes, Steve Ferraro in the chat asked, "What's the list price?" The UK price on the B&O website is £125,000.
A pair.
Oh, pair. Well,
You get two.
bargain.
Yes.
Okay, cool. Lots of greetings coming on the chat. But yes, first of all, thank you very much. This was brilliant comment from Forrest, the coolest talk he's ever seen. That was really good.
Thanks, Forrest.
So, yeah, brilliant. Okay, so let's just have a look at the questions that have come in. As I said, if you have any questions, please type them into the Q&A box below, and we'll ask our speaker, not loudspeaker, but our live human speaker, Jeff, to answer them. So we've got a couple of questions here to start with.
Yeah.
And Sergey Dombrovskis, I hope that's pronounced correctly. How do you choose the target for speaker dispersion width? Do you have some target, or it is random as long as it's smooth off axis?
Initially, we didn't have a target until we built something and found out how it behaved. And as I said, with that version that had the cluster of 5 on the front, in the end, it turned out that was too narrow. And I'm sorry, I don't know how many dB down we were on that speaker off axis. I know we ended with Beolab 90 at 20 dB down at 90 degrees off axis. If I were making a pair of Beolab 90s just for me, and I wasn't married and I lived alone and I had no friend, well, I have no friends, but if I didn't invite anybody over, I would prefer a narrower dispersion, meaning a narrower beam. But one of the disadvantages of that version that we made, the third prototype that you saw, was that you were really stuck. It was a bit like the effect, if you've ever heard really large electrostatics, where even though we were controlling the directivity very carefully to be frequency independent, it was still very obvious, even with small movements in the chair, that images would swing more than normal, whatever normal is. And we all know that when you're sitting between a pair of loudspeakers and you're listening for the center image, of course you get a swing when you move to one side, because the time of arrival from the two speakers changes so dramatically. At least up here, we're pretty good at detecting time shifts. But for that version, and honestly, I wish I knew how tight that beam is. It was just too narrow to be usable by a normal customer. It was so narrow that we expected nobody would ever use it, because you were really locked down to that chair. So as I said, we are at 20 dB down at 90 degrees off axis. We can go back and look at the numbers. I can pull up that beam with on. So there we are. If I go back and start sharing my screen again, you can see the actual values. This is 14 dB down at, let's say at 1K, we're 14 dB down at about 70 degrees roughly. And like I said, our target was 20 dB at 90. In the end, it wound up being a big part of the sound design. In the old days, my job as a sound designer meant tweaking the frequency response. Oops, what am I doing? Am I doing something? Have I dumped off the?
No.
Okay, open system settings. Oh, I'm doing something now. Sorry, I might have lost you from the computer.
We
my Mac.
can still see your slides and your
Okay,
video.
then I'll stop sharing. How's that? Now you
Yep.
can see me.
Hey.
Okay, so what was I saying? Oh yeah. So in the end, so if I go back 10, 15 years ago, my job as a sound designer at B&O meant tweaking the frequency response, the magnitude response with filters. I don't do that anymore. Now it's designing the directivity. And so when we just came out with our most recent speaker, which is Beolab 8, which is a tiny little thing that also has beam width control, when the engineers came to me with the first iteration, which was their best guess based on the measurements of what the narrow beam width should be, we knew as soon as we started listening to it that it was too narrow and we had to widen it a bit. Again, it was based on how it sounded in a bunch of rooms rather than having some target as a number and just going for that blindly. I think that's the answer.
Cool. Got a lot of more questions. Let's sort of share the experience. So Greg White is asking, why did you create the mesh on top of the tweeters rather than using that volume for additional back volume?
The honest answer, you can easily see it. I'm going to take the camera and show you why. Because we have this speaker over here on display in our museum, and you can see right here somebody's poked their finger through it. And honestly, what we need is something. We need a mesh on top to keep people's fingers out. We all have children. Children have friends. It's a problem. In the end, the tent of which is the grill was a solution that the visual designers came up with. What we wanted was to make sure that the drivers were as close together as possible, and we got all the volume we needed. We didn't need more volume behind those mid-ranges. But then we wanted something that looked uniform, not only from the front, but also from the whole rotation. Because you can rotate the beam, the designers wanted to make sure that it looked like a 360-degree loudspeaker, so that it didn't look like there was a front. We didn't need more volume, so the head unit on top is as big as it needed to be acoustically, and then the visual designers were left to do whatever they wanted with the grill that sits on top.
Sure. Okay, next question from Robert Huot. Can you describe the conversation around giving so much control to the installers and owners?
Yeah, we have different types of owners. Let's start at the end and work our way back. So some owners just want to turn on their TV and sound comes out of the speakers and they're happy. Other people, we do have customers that buy Beolab 90s and don't have anything else from Bang & Olufsen. They only own the 90s and they've bought them as high-end audiophile speakers, and they want to have the same control that they some people pretend to have by having expensive wires and cats that live on amplifiers and things. So we needed a speaker that could perform both roles. It's a bit like having a car where you can drive it in automatic, but then you have paddles on the steering wheel to change gears if you wish. So we had to give our customers the options of doing nothing or playing with it if they wanted to. And both kinds of customers exist, and both kinds of customers behave that way. The installers are trained by us, and so they need to ensure that the customer gets what they want in the end. We're not trying to make a speaker and force it down someone's throat and say, you must have this sound, you must sit there. I've seen in some audiophile manuals, they recommend that if the speakers sound too bright, you should buy new curtains. That's nonsense. Our speakers have to live in a customer's house and they have to be happy with their purchase. And we use our installers to make sure that interface happens between what we do here and what they get. And so our goal through the installer is to make sure that the customer hears as closely as possible a sound in their living room that we hear here in the listening room when we're making the speaker in the first place. And we need our installers to help with that. That's why they come here every 6 months for additional training.
Okay, great. Now let's dive a little bit into the technical side of things. Question from Elena Bukafieva. Do you use any modeling software for design or only prototypes and listening measurements?
Back in those days, we didn't use any modeling software, not in the, like, I guess you're asking about things like Console. Nowadays, we use Console, or we're starting to. In those days, we didn't. Instead, what we're doing is using MATLAB to process the measurements of the real prototypes and then implementing filters to find out what the result will be. So it's not modeling software in the standard sense like Console is today, but it's also not, seat of the pants. We build a prototype, we measure it, we can see in the measurements what we need to fix in the prototype hardware and what we can fix using software, and then iterate on that. So I've shown you 1, 2, 3, 4 prototypes here, but there were many more than that. These were just the highlights, the peaks along the way. There were a lot of other prototypes where we tried rounded edges and sharp corners and different placements of things. We're always relying on real measurements of real things, plus what we know we can do in the processing to predict what we need to do on the next iteration.
Okay, great. And again, sticking with the more technical side, what is inside the cabinets? Do all the drivers share the volume, for example, the mid drivers, or do they have their own smaller spaces?
Yeah, I often tell people that putting 2 drivers in one cabinet is like putting 2 children in the backseat of a car. Someone's going to win. So in this case, all of the drivers have their own individual cabinets, and those cabinets all have the same volumes for the same drivers. So they don't, of course, we don't have the same volume on the mid-ranges as we do on the woofers, and we have 2 different types of woofers. So they have customized volumes. And then inside each of those cabinets, we have Rockwell or Bassotech, depending, to ensure that we don't have too big a resonance inside the cabinet. That reduces the magnitude and the Q of the resonance from the cabinet, which we can then deal with the rest in DSP.
Okay, brilliant. And the next 2 questions are kind of related, so I'll put them together. So, are the question from Forrest and another from an anonymous attendee. Are the 90s the peak of what can be achieved from the perspective of a consumer speaker system? Are we at the realms of diminishing returns for the sound it could produce?
I'm not sure if I can answer that question. What I can say is that we realized really early on, even before we started production, we were at the end of development of the Beolab 90, and we started running up against the limitations of the signals coming in. If a visitor came to Bang & Olufsen 15 years ago, maybe less, 12 years ago, back then, because our visitors have requests, they want to hear a song that nobody's ever heard before, we would use Spotify. Not for developing speakers, but for doing demos internally for visitors, because we had that option to take requests. With Beolab 90, we started hitting what we thought was a problem in the speakers, but it turned out it was the Ogg Vorbis codec with Spotify. So what we're finding now is the limitation most of the time, and I certainly won't say that this is the best speaker anyone can ever make. It's certainly the best speaker we could have made 5 years ago when we made it. I'm not sure what we would do differently today, because we'd have to start again and really dig our heads in and think about it. Of course, unless we've already started doing that, and that's something I can neither confirm nor deny. But what we do see with Beolab 90 is more than any of our other speakers, including the ones we have bought from our competitors, we can hear the limitations of what's being fed into them. That might be a streaming service, it might be the source, it might be the analog output of whatever we're plugging in. Usually, and I'll say like 87.2% of the time, what we're hearing with Beolab 90s, the problem is coming from the outside world, not from the inside.
And I guess, a sort of, yeah, a follow-up question, but I think you probably answered it, is if you would start today, what would you do differently for developing the Beolab 90?
I'm not sure. I think I would. The nice thing about the way we were allowed to develop Beolab 90 was that we took 3 years listening to loudspeakers in spaces, and that was audiophile speakers, that was normal speakers, that was studio monitors in studios. And for 3 years, we just went around listening to speakers and making a list of how we wanted this next flagship to behave. So we didn't start by saying we want to build a beamforming multi-way giant speaker with 18,000 watts in 5 milliseconds. We said we want the imaging of those speakers and the bass capability of those speakers. And that speaker that we brought around, we noticed it sounded like itself no matter what room we put it in. So we had this checklist of how we wanted the speaker to sound. And we then started, after 3 years of that, trying to figure out what did we have to build to deliver that list as closely as we could. I would start from scratch again and start listening to new speakers in new spaces and find out what are people using in studios today that they weren't using 10, 15 years ago when we started Beolab 90 the first time. And make that checklist again and see if it's changed. And then take it from there.
So very much back to the drawing board, start with a clean sheet again.
You know, that's what makes it most fun. It's not the fastest way to work, but it's the most fun way to work.
Excellent. Okay, and so as time is ticking on, here's our final question for the evening, departing a little bit. The final question from Sergey again. Could you please say a few words about directivity of speakers in car audio? It seems that waveguides are used only sporadically in high-quality automotive systems, unlike modern home audio.
Yeah, the big difference between I'm gonna fudge on this question a little bit and not answer it, but give you an answer that you don't want. The disadvantage that we have when we make a speaker for home audio is that we don't know anything about your home. So for Beolab 90, for example, we make this narrow beam because we assume you have walls and we assume they're reflective, but we don't really know. The advantage any company has in car audio is that you know exactly where the speakers are, you know almost exactly where everybody is sitting, you know a lot more about the entire system, the drivers, the capabilities, not the drivers, you know, the person driving, but the drivers like the mid-ranges. So you know more about the total system, even though it's worse, right? A car is a lousy acoustic environment. It's very noisy from the outside. The speakers are in the wrong places, but you know where they are. You know what the noise is because there are microphones everywhere. You know a lot. And as a result, you don't need to have the same kind of solutions to solve the problem because the problem is different. Waveguides get used in home speakers. Waveguides is maybe the wrong word, but at least our directivity control is used because we don't know where you're going to put them. In a car system, we know what's going on, and so we might not need the same tools to end up with the same result.
Okay. And just one final question, which Bill Gilhouse snuck in, and I think is quite an entertaining one. As an organist, are you disappointed they don't go down to below 20 hertz?
Well, Bill, I've got a bad answer for you because they do. The very first version that the engineers gave to me to listen to were EQ'd to go to 20 hertz. And I am an organist, and I complained, and the final version of Beolab 90 goes to 14 hertz. Thank you very much.
Brilliant. Well,
how did you know I'm an? Oh, I said I was an organist, right?
Yeah, someone has clearly been paying attention to your slides.
Obviously, hasn't fallen asleep.
Brilliant. Well, it just remains for me to say thank you to our speaker, Geoff, for a brilliant talk, and his able assistant who is behind the camera. It's not an automatic system, it's actually a real person.
Thank you, Jette.
Thank you to our audience for joining us tonight and with your great questions. Thank you to the AES for hosting this and making it all possible. So thank you again, Geoff. It's been a brilliant talk, and this will eventually end up on our YouTube channel at some point in the future. So lots of thank yous coming in over the chat. So I think, yes,
Great.
a brilliant talk, Geoff. Thank you very much.
Thank you. Bye.